Today we are talking about compressible flow, some preliminary aspects. Introduction is chapter 7 from the book. So what is compressible flow? Previously in aerodynamics, we studied flow which is relatively slow. We call it incompressible when the kinetic energy of the flow is not capable to change the density of the flow. And compressible flow is the flow which has this amount of kinetic energy, quite big one, which we study in gas dynamics. And we needed to determine the main difference between incompressible and compressible flow to improve our models and to be capable to calculate such flows. So the chapter 7 is having this structure here, as I show you on my screen, is a review of thermodynamic properties, which is talking about perfect gas, internal energy and enthalpy, first law of thermodynamics, entropy, and second law of thermodynamics, and isentropic relations. Usually I skip this part of discussion because it makes part of your previous studies, which you had before, of other disciplines, right? Starting from phenomenology transportje, fluid mechanics, and probably others. Right? I will just give you few very important relations which we will use, which we will constantly use in our lectures, in our studies and calculations as well. So then will be a definition of compressibility. This definition is classical definition of compressibility. Then we talk about definition of total or stagnation conditions for compressible flow, and then some qualitative aspects of supersonic flows with shock waves. We give some preliminary introduction, what are the shock waves and which processes happen on these shock waves and different types of shock waves. So as I already told you, the first part of the discussion review of thermodynamics is something that you probably know very well. And you can find not only in the Anderson book, but also in other books of other authors, other subjects which you studied previously. So what is important in these thermodynamic relations? First of all, is the main equation which we use is the equation of state. The equation of state that relates the pressure, density, gas constant, and temperature. Usually we write it in the following form. I will write it on the side of this slide. I hope it will be also visible. Pressure is equal to the density multiplied by gas constant and multiplied by temperature, where all these parameters should be calculated in C units, right? They cannot be calculated in other unit different from C because each of them has its own dimension. Usually here pressure we use in Pascal, density we use in meter, in kilogram per meter cubic, right? Gas constant is joule per kilogram Kelvin, and temperature in Kelvin. Right? Please, very common problem when students use temperature in degrees centigrade or degrees Celsius, and they start to receive very, very big problem on their calculation. So we need to pay attention when we are using equation of state in this sense that the parameters are having their definitive dimensions. Of course, this equation exists not only in C units, but also exists in imperial unit. But then we use another conversion factor. Let's say this conversion factor is shown in the Anderson book. And with no problem, but since we are using C units for all our calculations, it would be nice if you continue this tradition. Okay, gas constant here in this formula, reminding you, is approximately universal gas constant divided by its 8314 divided by molecular mass of gas, which is equal for air 29. And when we substitute here the air molecular weight, we receive 287. This is joule per kilogram Kelvin. Okay. 287. If it's not visible, please ask me again what is the number I'm writing. From this equation of state, we usually have another form which has a relation between pressure and specific volume, gas constant, and temperature. Is pressure specific volume multiplied by, equal to gas constant and temperature. From this equation, we easily can find temperature or pressure or specific volume, or even gas constant if you don't know which gas we are using, but we know other parameters. Here, specific volume is a quantity reverse proportional to the density. It's 1 divided by 4. Okay, this is about perfect gas, the most important thing, but you probably already knew it, right? Then for the internal energy and enthalpy, we use definition of internal energy. Okay, I will put here that internal energy E is CV multiplied by T, where CV is the specific heat for the gas at constant volume, and T is temperature. And enthalpy H is very similar, but already Cp multiplied by T, where Cp is specific heat at constant pressure multiplied by the temperature. So these two parameters we are using. Between Cp and Cv, we also have relation. I hope you remember. But if not, I will remind you that difference Cp is always bigger. Cp minus Cv would be equal to gas constant R. Okay, and there is also another relation to the adiabatic coefficient. Cp divided by Cv is gamma, adiabatic coefficient. Adiabatic coefficient for air is equal 1.4. This is constant for low temperatures until approximately 1500 Kelvin. After 1500 Kelvin, when we start usually to have processes of dissociation, recombination, or hypersonic flow, this gamma starts to change and change significantly. This question we will discuss in one of the following chapters when we talk about hypersonic flow. Okay, that's these are relations. We can see these two equations as a system. We can solve them together as a system. And if you open Anderson book, equation 7.9, 7.10 gives us a relation between specific heat, gas constant, and adiabatic coefficient for both of these parameters, Cp and Cv. This is one of the ways why we are talking so much. The main reason is that Cp and Cv usually you do not need to to define directly, right? When you know adiabatic constant gamma and when you know which gas you are using with known molecular weight, then we can calculate Cp and Cv for any gas. So we do not need to use any other reference. Again, I would like to remind that this is valid for small temperature until 1500 Kelvin. And after, it's another story we will discuss. So just to finish the logic of this discussion, I will give you the formula from the book that Cp is gamma R divided by gamma minus 1, and Cv is R divided by gamma minus 1. We can see they are very similar. These functions, just Cp and Cv, they are proportional one to another and differ by this coefficient gamma, right? Which is always more than one. More than one. Very important observation, because in many formulas we will see in gas dynamics. Let me choose another color. In many formulas, this gamma minus 1 will be always present. And when we subtract 1 from some number which is more than 1, we always receive positive value. Okay? It means that Cp and Cv will always remain positive. So physically, we are correct. Be careful, do not use gamma equal to 1 in such calculations, because in real life, gamma equal to 1 does not exist. And this would mean that you will have infinite value of specific heat, which is also physically not possible. Okay, Anderson is giving to us inside example 7.1 some samples of calculation of parameters of perfect gas, internal energy, enthalpy. So if you are interested, you can follow and see which numbers could be obtained. But in general, I see no reason for us to spend time, and you can study this alone. Or you already know how to calculate because you finished previous subjects. Okay, about first law of thermodynamics, I think that you remember, right? That first law of thermodynamics gives us some relation between change of energy in the system, that is changing due to added heat and work, right? This is also no need to repeat, and for my opinion is quite clear. And as a consequence from the laws of thermodynamics, especially from the first and second law of thermodynamics, we start to receive enthalpy change when the flow, or sorry, entropy change when the flow is not isentropic. The entropy change characterizes for us, let's say, losses or transition in the system, which can be related to the losses. And this can be calculated according to thermodynamic relations, is equation 726. I will show you this equation right now. This equation right here. Okay. I hope it is visible. I think some pictures or some equations I will just drop on the screen because it's much simpler to do in this way than to write long relations, and then we can discuss other things. Please, if you or someone asks questions, Let me know. For now, I see no questions, so I will continue this explanation. As a consequence of isentropic relations, we have ratios between different thermodynamic properties inside the gas. I hope you know the main isentropic relation. Okay, probably before definition of compressibility, I will put it right here. This relation corresponds to the equation 732, which talks about change of thermodynamic properties into different points inside isentropic flow. Isentropic flow, so the flow which has zero change of entropy. This is the formula which gives to us change of entropy 726, right? And if this is zero, then isentropic relations start to work. It says to us that in two different points, for example, ratio of pressure would be equal to the ratio of densities in power of gamma, or will be equal to ratio of temperatures in the power of gamma divided by gamma minus 1. Also, we may find here this gamma minus 1 is present, right? Gamma minus 1 is present, so this ratio is always positive. And look what we also can find from this relation. Probably you already know that since let's assume that pressure 2 is bigger than pressure 1, it means that density 2 will be also bigger than density 1, and temperature 2 will be bigger than temperature 1. So all parameters, all thermodynamic parameters, they usually change in the same direction inside isentropic flow. We will see this soon when we talk about flow in the nozzle and calculation of the flow in the nozzle. There you will see that they are, let's say, similar changes of pressure density and temperature inside the nozzle, which is quite important to understand since the beginning before we start to go to the nozzle section. Example 7.4 and 7.5 give us another possibility to calculate change of thermodynamic properties according to the relation I just showed to you. I think you can check. And main definition of compressibility is shown on this screen. Definition of compressibility is very important, and as I already told you, for fast flows, the coefficient of compressibility is called tau, which is reverse proportional to the specific volume and proportional to the derivative of specific volume by pressure. This compressibility coefficient can be defined for the arbitrary case as shows equation 733, or can be defined as a function of, not a function, for isothermal process, isothermal compressibility coefficient, tau T, or can be even calculated for the isentropic compressibility coefficient, tau S, where in the first case, we have partial derivative of specific volume by pressure for constant temperature. And for the second case, specific volume derivative by the pressure at constant entropy. Okay, so schematic at figure 7.3 shows change of the volume, right, and change of the pressure, because change of the volume can be caused only by change of the pressure. Sorry, change of volume can be caused by change of pressure. Another formulas which you may find in the book are mainly transformation equation. 737 is the reorganization if we would like to obtain the differential of density, would be a function of density compressibility coefficient and differential of pressure. It's just a rearrangement of the equation 36. And another equation which we may see is a definition of Mach number, which is velocity divided by the speed of sound. Why actually we use definition of Mach number, we will see very, very soon. And for us, Mach number, or relative velocity of the flow to the speed of sound, characterizes kinetic energy of the flow. Till now, I see no questions, so I can proceed to the equations for Inviscid compressible flow. These equations you saw many times. Probably I will stop on some aspects which we are discussing in following chapters. I would like to remind you that Anderson already presented before the equations of the flow general in the book. And you also studied these equations in the other books, right? They are typical flow equations that can be called also Euler equation system or Euler equations. And these equations, they do not have viscous part, so they are inviscid equations. These equations have the time part, the time derivative, so they are transient equations, right? Not stationary. So something we preserve. Equation of the flow can be written in general in two different forms. Integral form, like equation 39, and derivative form, which is equation 40. Which is the difference between them? Is how we try to calculate the flow process. Integral form, equation 39 and similar, is looking to the flow volume as a big control volume, right? One control volume where we are looking for the balance. In continuity equation, it will be a balance of mass. In momentum equation, it will be balance of forces. In energy equation, it will be balance of energies. So balance as a global parameter. And in differential equation form, like equation 40, we're looking at a microscopic level to a finite element, which is infinitesimally small volume. And inside this volume, same or similar processes happen as in the big volume, as in control volume. When we summarize all the finite elements, all the small elements, we receive a big element, a big volume, a control volume. So equation 40, as you remember from aerodynamics, is usually received from equation 39. So they are equivalent in some sense. At least we always can receive equation 40 from equation 39. Right? Both of these equations have several parts. For example, continuity equation. Continuity equation has a part which is transient, right? Describing how mass of gas is changing in time inside the volume, which is integral by volume of density, right? When we integrate density inside space, we receive mass, and then we apply time derivative to this mass. We see how this mass changes in time. And this quantity of mass change in time is equal to how much of this mass passes through the wall of the control volume. So this is an integral, a surface integral of density multiplied by velocity by surface. So when we calculate this product, it also gives us mass. So mass on the left side of the equation and mass on the right side of the equation. Do not forget that all the units in all parts of the equation should be absolutely same. So we can not summate, for example, kilograms and meters. It's not possible. Multiply, of course, we can, right? What happens when we do this? We receive another quantities, another units, right? For example, when we divide mass by volume, kilogram per meter cubic, we start to receive density, right? But when we try to make a sum of mass and volume, this will not give us anything. There is no sense. Here, same thing. So each part of the equation has absolutely the same dimension. In this part here is kilogram per second, right? This first part. So it means that the second one will be also kilogram per second. Because inside velocity, we have meter per second. So second is present in the right and left side. If you have doubt about this, please let me know. And in some next discussion, we can touch this question, but I hope it was quite clear on other subjects, and also Buckingham-P theorem, which says us which dimensions we could use and how to multiply and find the dimensionless criteria for the flow, also answers this question about dimensions. But if still not clear, we can discuss in the following classes. So change of mass inside the volume by time, and this change happens because of flow of this mass through the surface. So mass balance total is equal to 0. So once mass is coming, this mass is coming not from nowhere, but this mass is coming from surface, and total global balance is always 0. It's a fundamental, I think you already know quite well, that in any model, we must have an equilibrium of quantities, for example, mass equilibrium or momentum equilibrium or energy and theta. There are many different equations with many different parameters. Unfortunately, we do not study in this course other forms of flow equations. But if you find another literature on aerodynamics and especially flow mechanics, you may find that flow equations, they can be written not in these normal parameters that we know, like thermodynamic parameters and velocity, but also can be written in absolutely different parameters like enthalpy and streamline function, entropy function. So there are many parameters we can use to rewrite same equation system. It depends what we are trying to solve and which method we will be using to solve this equation system. Talking about momentum equation. Momentum equation has absolutely same logic that the continuity equation, just more complex, right? You remember that the total force is equal to 0. So left part of momentum equation 41 is representing to us change of momentum by time inside the volume. Momentum is calculated as a product of density and velocity, right? And the flow of this momentum through the surface of the control volume. On the right side, pressure forces. Pressure which acts on the surface of the control volume creates this total force. And surface forces expressed by F coefficient. Right. Usually, surface forces are proportional to the density. So density is outside of F. In any of our applications of aerodynamics, we will never work with surface forces. Right. But in some specific applications where, for example, we can have sources of momentum, let's say different applications, we will need to deal with this question. Momentum equation written in integral form and momentum equation written in differential form actually split in three different differential equations in substantial derivatives, because V in this equation is a vector. So when we are trying to write the algebraic equation, we need to split this vector in three different quantities if the flow is three-dimensional, or at least two different equations when the flow is two-dimensional. In our case here in general is three-dimensional momentum equation. Energy equation is the most complex equation among all flow equations because it uses definition of energy, and energy is not defined as one parameter. Energy can be kept inside kinetic part and potential part. The kinetic part of the energy is hidden inside velocity, so we can see it in several parts of this equation, right? And the potential part of energy is hidden inside the temperature. And we also can see the internal energy in different parts of this equation. The idea of energy equation is similar to the previous equations. It says that energy does not go anywhere and does not appear from anywhere. Energy only transforms from one form to another. Here we have a global energy balance in time, change of the energy in time inside the control volume. Here we have how energy flows, this relation, how energy flows through the surface of the control volume. I would like to remind you that this energy here in brackets is a relative energy. It must be always multiplied by density, because to receive the real energy, we must multiply relative part on the coefficient. Density is not only the characteristics of mass, but also characterizes as density of energy. Essa derivada d por dt é a derivada material sim. Em inglês chamada substantial derivative. Okay, substantial can be written in ordinary derivative. I think this topic of ordinary derivatives and substantial derivative Anderson explains quite well in the first part in aerodynamics, so you're supposed to know already. Just I think I can give you just a moment. I can give you a page where is written this question. Is inside probably second chapter of the book, and and somewhere here. Just a moment. The second chapter of the book, and if giving for different types, for different equations, for continuity, momentum, and for the energy, for energy equation as well. And I'm just trying to see where it's given. If I cannot find, we can keep it for the next time, because I do not want to waste time just looking for these definitions. Yeah, the substantial derivative is the sum of time derivative and space derivative. I hope you remember. Unfortunately, I cannot find right now at this moment, but we will return to this question next lecture, and I will show you the formula. I just don't want to mistake and give you a wrong relation. Okay, let's keep it for the next time. Is a total of time and space derivative. Okay, so where I stopped on the sources, right? On the sources of energy. I will remove some parts, a bit a lot of things, right? So flow of the energy by the surface. This here is change of energy due to the chemical flow process, or is called source. Energy source can be chemical source as usual, but also can be electromagnetic energy source, can be other source of energy. Also, this source of energy is usual, happens inside all the volume. All right. This one is the energy change due to the pressure forces. And the last one, energy change due to the surface forces. And the energy equation can be given also in a differential form. How to make it, Anderson explains, as I told you, in the second chapter of his book. Let's see, we had three equations, right? The continuity equation, which has inside the density, velocity, right? Two parameters, density and velocity. The momentum equation has density, velocity, but also pressure, already third parameter, right? I show you two equations, but we already have three parameters, three independent parameters. Energy equation, it has, despite of density, velocity, and pressure, we have internal energy. And inside this internal energy is temperature, right? So many parameters, more than number of equations. This is why to close the equation system, to complete the equation system, we need two more additional equations. They are equation of state and internal energy equation. In such way, the number of unknown is equal to number of equations, and this equation system can be solved. It's quite important for us, for applied science as a gas dynamics, to have the equation system, or to have equation system which can be solved. which can be solved. We need to solve. Okay, I hope this is clear. At least I do not see any new comment. Please, if you have some question or comment, do not forget to use Teams and write me this text while I'm discussing next subject. Our next subject is definition of total, or they are called also stagnation conditions. Why total and stagnation same time? Is it's the same word, it's synonym, but in some books you can find total conditions. In other books you will find stagnation conditions. It's same thing. What is this total and stagnation conditions? Probably you remember, but I will try to remember you. But if we have a flow, at some point will be a wall, okay? And on this wall, flow will stop. What will happen in the real case is the following. Flow will go in two different directions, but at the very center point, very central point, the flow will stop. So when we had V infinite here, on this point, we will have V equal to 0. Velocity will be 0. Flow will not move. All the kinetic energy from infinite distance will transform to potential energy. And it's very important to us to calculate properties at this specific point where flow is stopped. It is not only to know how big would be the pressure, density, and temperature, not like this. There are even examples when flow does not stop. We will see them, for example, inside the nozzle or inside the diffuser. Flow doesn't stop, but we need to calculate stagnation conditions because stagnation properties, they are characteristic properties of one or another structure. Even by definition of stagnation parameters, we can calculate efficiency of one or another structure. So let's see this question precisely. How to calculate stagnation conditions? We need to see again our energy equation 45, and inside this equation 45, we will rewrite the right part of the equation on the pressure contribution, right? And according to the formula, which gives us derivative of complex function, we can see that the product of pressure and velocity would be, a derivative from the product of pressure and velocity would be this relation, this big relation, right? And then we go back to our energy equation, make some transformations, and obtain very, very important relation that for the flow, this sum of enthalpy and velocity in square divided by 2 would be constant. Constant because right part of the equation, all this part is 0. So inside the derivative, we need to also have derivative equal to 0. It means that inside the derivative, we have a constant parameter. Again, to remind you, this part here is enthalpy. Okay, it is enthalpy. Internal energy plus pressure divided by density is equal to enthalpy. Then we call this constant as stagnation enthalpy. Okay, and we say, okay, stagnation enthalpy is constant. So the stagnation enthalpy is constant for isentropic. It may be not also. Isentropic flow. This is the main This is the main parameter, or let's say property of the flow we will use to estimate stagnation conditions. So we are looking to the stopped flow as a flow with the constant enthalpy, which is maximum possible enthalpy for the system. We may find 4 different types of flows, as you already know. They are non-adiabatic flow, when we have many processes that, for example, account on heat transfer with the wall with some external bodies, or adiabatic flow. The second case here, where we assume that inside our flow we do not have heat exchange with external bodies or bodies inside our system. In such case, stagnation enthalpy is preserved, and since stagnation enthalpy is proportional to stagnation temperature, just to remind you that enthalpy was given previously as Pp multiplied by T, so it's quite obvious if I write 0 right here, and then I can write 0 right here, but nothing changes, right? Cp is constant, so is the value which does not change. It means that if for some flow adiabatic enthalpy does not change, then so stagnation enthalpy does not change, and then stagnation temperature also stays constant. A very good, very nice observation that helps to use different forms of energy equations, which we will see soon. Then there is also non-isentropic flow and isentropic flow. There is the difference. I hope you already know or you remember from previous classes that isentropic flow is the flow which is adiabatic. It means does not have heat transfer with solid objects, and this flow is also reversible, so it can go in one direction or can go in the other direction without any change of entropy or without any losses. In this case, we have preservation of stagnation pressure and preservation of stagnation density. What is stagnation pressure? Stagnation pressure is the pressure which we have when the flow stops. So if we stop the flow in one point, in point 1, make a bit zoom. If we stop flow inside point 1, we receive some stagnation pressure. We stop flow at point 2, we receive another stagnation pressure. For isentropic flow, these two pressures of stagnation will be same. And also densities of stagnation will be same. Stagnation density is the density that happens when flow stops. It's quite obvious. So we have stagnation pressure, stagnation density, stagnation temperature, and stagnation enthalpy. Can be this word stagnation can be written in front of any thermodynamic parameter. And the opposite non-isentropic flow, where we have flow irreversible. In this case, unfortunately, stagnation pressure cannot be conserved, stagnation density cannot be conserved, and this is one of the questions to be solved inside theory of normal and oblique shock waves. It's solved analytically, and also in case of hypersonic flows, unfortunately cannot be solved analytically, can be solved or experimentally or numerically with the, let's say, big difficulties. So this is revision of 4 main types of flows. Of course, from point of view of calculation, for us is always favorable or more interesting to have isentropic flow, because it allows to calculate quite easily almost any type of the any geometry of the flow. In some cases, adiabatic, they are very nice because with the assumption that we have no heat transfer, also model is not so complicated. As I already told you, non-isentropic flow is probably the most difficult from computational point of view in some cases, but in some cases, as we will see, it can be obtained analytical solution, and we will use it particularly inside work 1. Okay, I do not see any questions for now, and I think we can proceed. Inside example 7.6, you may find how to calculate total temperature from known other parameters of the flow. This question we will also touch on the next discussions, because when we see the equations, algebraic equations for isentropic flow, then we will talk about such calculations. So we will not miss this equation, this example 7.6 and 7.7. We still will return to this question, and I will show you how you easily can calculate isentropic parameter or stagnation parameter. The last part of chapter 7 is aspects of supersonic flow, shock waves. Just a moment, I will take a look if I did not miss anything. No, looks like we discussed all what is required. Chapter 7 is quite short, and we will finish today. Next time, we will start already chapter 8. Okay, so shock waves. Just if we see what is the shock wave, could be nice. The shock wave is a structure that significantly and suddenly changes the flow. There are different types of shock waves. We can determine at least 2 main types, which is oblique shock wave and normal shock wave, and there is also combination between them, as you will see from next discussion. There are also so-called bow shock waves, but this is another story, another question. The problem of other types of shock waves or lambda shock waves, that these shock waves cannot be calculated analytically and can be only studied in experiments or numerical simulation. For me, probably you already understood that numerical simulation and experiment is almost the same thing. Right, we can have such a good quality of simulation sometimes that experiment will coincide practically 100% with simulation. So it means that we are doing virtual experiment. In this case, numerical experiment, we can call the process of numerical simulation as numerical experiment. These 2 types of shock waves, which you see on the screen, they are shock waves relatively simple, and they can be calculated analytically, and you will do it inside work 1. But before, of course, I show you how to make such calculation, and the more important, how to elaborate equation system for such calculation. Let's see, oblique shock wave is usually generated when we have a body not normal to the flow. For example, we have some thin shaped body. I will try to draw probably like this. Okay, we have a body, something like this. Some aerodynamic supersonic flow requires sharp edges. For example, we have this kind of airfoil, quite exaggerated, right? The thickness, but just to show you that sharp edge is generating the oblique shock wave. Oblique shock wave is a shock wave which is not perpendicular to the flow. Normal shock wave is a shock wave which is perpendicular to the flow. Normal shock wave can be generated when the surface of the body is also normal. For example, we have some spherical object or semi-spherical object with the surface quite normal to the flow. So this normal surface will create such disturbances inside the flow that will generate a shock wave perpendicular to the main flow direction. More detailed about which type of the shock wave exists, we will speak respectively in the normal shock wave section and in the oblique shock wave section. We will see that for oblique shock wave must be satisfied several different conditions to appear this oblique shock wave. It's not just to have a sharp body and supersonic flow. No, we need to satisfy several conditions, and all of them can result in oblique shock wave. Otherwise, they can result in normal shock wave or in a bow shock wave that we will see in some of next lectures. Oblique shock wave is not isentropic process. In transition through the shock wave, entropy increases, as you may see from figure 7.5. Entropy after the shock wave is always bigger than entropy before the shock wave. Entropy is S. Okay, S is entropy. Other parameters here: M Mach number, V velocity, P pressure, O density, T temperature, P0 is stagnation pressure, H0 is stagnation enthalpy. In both of such structures, thermodynamic parameters increase. We may see it here: pressure, density, temperature rise in both of such shock waves. Pressure always, temperature, and density rise when flow passes through the shock wave. It's not possible to reduce thermodynamic parameters in such process, not possible. So when you receive inside calculation that your parameters decreased, you can be 100% sure that calculation was wrong. Parameters can only increase when flow passes through the shock wave. Velocity always reduces in both cases, as well as the Mach number also is going down. Inside oblique shock wave, Mach number was supersonic and remains supersonic. Here, M2 more than 1. In normal shock wave, Mach number was supersonic, and after the shock wave, it will be subsonic. It will be subsonic. So this is difference with respect to oblique shock wave, subsonic. So here subsonic, in oblique shock wave is always supersonic. To appear for any kind of shock wave, you need to have supersonic flow before the shock wave. For subsonic flow before the shock wave does not appear, cannot appear, because of physics of the shock wave, which we will discuss very, very soon, I hope, next week. Okay, let me see which things we still need to to discuss, I think, is these photos that prove theoretical models. The photo of ball shockwave. Usually shockwaves cannot be just that simple as I showed you on the previous slide, but as I told you, can be of a complex shape. Shape of the shockwave is strictly related to various factors. Main of them are Mach number before the shockwave and the shape of the body. More complex shape of the body, more complex will be the shape of the shockwave, but it will never repeat, let's say, proportionally, nothing like this. Shockwave and compressible flow are highly nonlinear processes. It means that the flow cannot be described by any kind of simple equation, right? Especially such complex shockwave, which we see on the screen, can be obtained only experimentally. And if we are very lucky and very good in numerical simulation, we can obtain them numerically. Here I want to show you this part B of the picture. You can see that shockwave distance is very small to the body. It's saying to us that very important is the shape. In some shapes that we will discuss in gas dynamics, shockwave will never even exist. Such shapes are perfect aerodynamic bodies that are called isentropic bodies or isentropic nozzles or isentropic supersonic diffusers. In such structures, shockwave do not happen, or they happen in such way that they are infinitesimally weak, very weak. Why I do not like shockwaves? So it doesn't mean that I do not like shockwaves. Shockwave is not very good for the aerodynamic structure, but in many cases, shockwave is the only way to have flow in the structure. For example, if you have a supersonic, sorry, my screen turned off. I will start again. In some cases, when we need to have flow, to decelerate, for example, to decelerate from supersonic to subsonic, there is no way not to have a shockwave. In other cases, there is a way. We will discuss it in a section of nozzles and supersonic diffusers. Okay, my screen already appeared. Let me share. Shockwave by itself, from performance of aerodynamic processes, is not a good thing. We always try to avoid shockwave or to make it as weak as possible, because shockwave reduces the energy of the system. Increasing the entropy, we significantly may reduce the global energy balance, and some structure will not fly. For example, this is critical when we are trying to create a scramjet engine which flies in very high velocity, or in hypersonic engine, right? Scramjet is the engine which allows to fly in hypersonic speeds. I think recently Brazil tested one of such engines inside one of the projects of military applications. We're always trying to reduce the strength of shockwave. As fast we would like to fly, more we need to work on making more performant geometry or regime of the flow. And only such measures will allow us to have losses in a level that allows to receive positive thrust and accelerate until some required velocity of the flow. Another visualization of shockwave is here is not so much clear because they are quite old photos, also Schliering photos. And especially I like this space shuttle photo on the inside aerodynamic tunnel, and you may see that one of the most important questions on the space shuttle design was re-entry problem. When we have hypersonic re-entry, temperature increased significantly, and in these conditions would be important to make a lot of calculation and a lot of experimental tests. Of course, you cannot launch complete shuttle in space and see how it will hit and do it every time, like Elon Musk is doing. But on those times, one of few possibilities were to test such a structure in the wind tunnel, supersonic wind tunnel. And here, this color on the body represents heating of the model of the space shuttle. There are different paints that can be used, some paints that change color when you apply heat. So can be visualized, naturally visualized change of temperature on the surface of tested objects. Just a moment, I will see. No, there are no new comments. Okay. This is the end of chapter 7. It's, as I told you, quite small, quite short. We could make it in one class. For today, I am expecting your questions. If you have some questions about chapter 7, other topics that we already studied before, or plan of study, or another questions related to our subjects, please ask now or type in the comment. I can wait some time. And if will be not so many questions or will be no questions, we could finish for today. And next time we meet as expected in on Tuesday, same time. I think there is no any comment. No questions? Okay. I will consider as the silence as no questions. Please prepare sometimes question. I will be very happy if you have some very simple thing to ask. Usually simple question is the most difficult question because it's hard to answer simple questions. Right? So I hope.
Professor.
Okay, please.
Você pode voltar naquele slide que se compara as grandezas termodinâmicas antes e depois da onda de choque, por favor? Isso, esse aí. Assim, nesse caso que você está mostrando, o senhor comentou que a onda de choque ela é simplificada, né? Tipo, ou a normal shock wave ou oblíqua. Nos casos dos exemplos ali, a gente viu um formato, assim, uma curva, alguma coisa nesse sentido. Só que, assim, localmente, a gente pode simplificar ela ou para essa normal ou para uma oblíqua. Não é o caso ou não? Tipo, se a gente for olhar, por exemplo, a gente tem uma curva ali no... a onda de choque é curva, né? Só que, assim, localmente, a gente pode aproximar ela por um dos dois modelos, não é?
I hope sometimes we can do it. Sometimes, not always, because
Ah, por exemplo, aqui tem um finco, né? É verdade.
Low parameters, they not so much linear, right? And they depend, each point depend on many other points. For example, when you start to change the flow, these perturbations, okay, these changes, for example, we have changes right here on this point. So these changes will start to influence on all points, and it means that they can also influence on formation of the shockwave. So when we are looking to the shockwave of complex shape, we need to be more careful, than just to see a shockwave as a normal or oblique shockwave. It also has relation to other points in space which we probably did not consider.
Então, por exemplo, essa análise dos parâmetros termodinâmicos e tal, a gente já não consegue fazer quando
I think with the simplifications, we can try to do it, but every time we try to adopt one simplification, one assumption or the other one, we need to be sure. So need some validation. And I think this is a fundamental aspect to validate the model, right? We cannot simplify so much as I think, but if we are working, for example, a long distance, one point is far from another point, then theoretically 2 points will not be so much connected. Of course, they will be connected, but not so much. We will talk about perturbations and the distribution of influence in probably already next lecture. So I will give you more detailed answer on this question because we have in the book some pictures that display this question. Okay? But in general, always need to check if we can do it or not. Experiment will answer or simulation will answer. You know, nowadays having very powerful tools of numerical simulation, if we look just on the part of shock waves, is absolutely not a problem to calculate if we have just this process of shock wave formation. Just put inside the numerical software, apply correct method of solution, correct model, and you will receive shockwave structure. Very nice to compare with the analytical solution. This is what we will try to do in our work here. But when we see more processes, for example, this shockwave generates lots of heat, and this heat makes regression or degradation of surface of the body, or the body is changing or moving, then is absolutely different question. Then, of course, simulation cannot be so simple, right? So depends on the number of processes we are looking for, depends on what we would like to take into account and what we would like to receive as a final result. You know, all Anderson is like this. The book of gas dynamics and aerodynamics is like this. We see different cases, and we try to adapt every time our model to those conditions and purposes of our calculation or simulation, and we start to understand if we are going in correct way or not. So, but I hope in some cases we can do as you suggested. We can assume some parts of flow as normal and oblique shock waves. I hope. Yeah, sometimes it works, sometimes it doesn't work. We need to see each separate case. But thank you for your question. Okay. Question from Marcus. Changing geometry is not possible to avoid all shock waves. As we will see very soon, changing the geometry, you can make shock waves less harder, or let's say more favorable for the flow. It means that shock waves, we can move from one position to another. So it means that they will hit our body in some specific points where we want them to stay, because in some place we don't want. If this place is very critical from thermal point of view, we don't want extra heating, then we need to move shock waves to another position. So moving the shock waves is possible with change in geometry and optimization. Losses, general losses or global losses in the system, we also can changing the geometry. Cases where I told you about isentropic nozzle or isentropic diffuser, they are very specific cases. They are ideal cases, right? In such geometries, we can reduce shock wave strength until the smallest. Okay, the shock wave will be very weak. The energy of the shock wave will not have almost any impact on the body. But in real case, shock wave will always be present. Even very weak, the weakest shock wave will be present. We can see it also from the following point of view. Any body moved inside the flow or put inside flow will have a boundary layer. Boundary layer stops flow completely, so velocity is zero on the boundary layer. Anyhow, it's not possible to have moving velocity, not zero on the surface of the flow of the body. So, and far from the body, we have, okay, here we have velocity zero on the boundary layer, and here we have infinite velocity far, or not high velocity, let's say. So in some way, this transition should happen. It's not possible not to have this transition. So because we have 2 points in space, flow will pass somehow, and it will create some structure, right? Even having presence of shock wave already creates preconditions to obtain shock wave. It's not possible to decelerate flow without any kind of losses, right? So losses inside the boundary layer will happen as well when we are moving shock wave on the region near the boundary layer is called shock layer, but also this very thin shock wave can reduce the global energy. So efficiency of real structure will never be 100%. In many calculations, it will be 95%, 99%, 99.9%. So we can neglect so small difference of small losses, and we will say our structure is perfect, and it does not have a shock wave analytically calculated because it creates very small perturbations that we can neglect. But in real flow, of course, these perturbations will exist. If not important for us, we ignore something, right? When things become more and more big or greater, we cannot ignore them anymore, and we need to take into account. Question about interaction of boundary layer and shock wave will be discussed also on this course. So if you will have these questions, we can discuss in one of the future lectures. Another questions, please. Please read the book. Take a look on chapter 7. I think it's almost everything I explained from chapter 7, but it's always nice to take a look on the book and see more additional information, especially examples from the book. Next time we will go to chapter 8, which is devoted to normal shock waves, and then we will already see how to build model of normal shock wave, simplest type of shock wave, and how to calculate such a shock wave. Thank you very much for today. Have a nice end of the week, and we will meet next week. Thank you. Bye.
Tchau, professor. Muito obrigado.